Hello, and today's purpose of the day is I can determine if a set of data displays exponential behavior and describe transformations of exponential functions. First thing we are going to do is we are going to review the different types of functions we are familiar with: linear, quadratic, and exponential. So let's look at linear first. If I want to write down some characteristics of a linear function, let's first remember the parent equation. The parent equation is y equals x. Right? So the exponent on x is 1. This is linear. It will eventually be a straight line. If I were to make a table of values and plug those in, let's say I plugged in -2, 0, and 2 in for x, I would get the following outputs for y: -2, 0, and 2, obviously because they equal each other here in the parent equation. And if I were to draw that, I would get a straight line like this. And you can see that straight line on the graph provided at the right. The general equation for a linear function is, we know y equals mx plus b, right? That would be slope-intercept form. We also have standard form of ax plus by equals c. Those are just some general forms. We also have point-slope form that we could write down. Some properties about the linear functions. Those would be, we have a straight line. It also goes on forever. That line does. And we could say more about that, but that covers the basics. The domain for linear equations, again, for all the x values, we have all reals, or x is between -infinity and +infinity. And we have for the range, for the y values, is also all reals. It goes on forever, and it's going to continue to go upward and downward, so it'll, hit every span of numbers. So y is between -infinity and +infinity as well. And this is just a recap of linear functions. Okay, let's take a recap on quadratic functions. And if you can recall, the parent function, or the parent equation for the quadratics, is y equals x squared. Or we could even say f of x equals x squared, so different notation. If I were to plug in a table of values for x, such as -2, 0, and 2, I would get the following outputs for y: 4, 0, and 4. Now, if I were to graph this over at the right, my graph would look like this. And on the graph, we have a parabola. So that's what the graph of a quadratic is. And we know that. General equation for quadratics, so if we remember standard form, we have y equals ax squared plus bx plus c. We also have vertex form, which is y equals a times the quantity x minus h squared plus k. Some properties on quadratics. We could say that we have, a U-shaped parabola for the graph. Parabola. We also know that parabolas are symmetrical, and we have the axis of symmetry to prove that. A degree of 2 in quadratics. It's a degree of 2. Domain and range. So for the domain, for the x values, we have all reals. So again, we could write that as x is between -infinity and +infinity. And then the range here, it depends on, each equation that you have and what the vertex would be, so the minimum or maximum. But in this case, for this parent equation, our range is, we go up to +infinity, but what's our lowest value? Here it would be 0. And again, y can equal that value because that is part of the graph. That's the vertex. So again, that is part of the graph, so we can equal the lowest value here of 0. And this was just a review on quadratic equations. All right, so a little recap on exponential functions. And I know we've only seen exponentials now for just a short time, but let's review the certain characteristics of exponentials. So the parent equation of an exponential is y equals a times b to the x, right? Where a and b can both be numbers, but our exponent x, that's our variable. The general equation is the same thing. Y equals a times b to the x. Now, if we were to try and graph this general equation, or the parent equation, we really can't, because a and b are both variables, and so is our exponent x. So there's no way really of telling what this would look like. So we have to actually pick, just a simple generic equation that we could use here to describe an exponential function. So let's just use the one we used yesterday, just to review this quickly and remember some of the characteristics. So let's look at y equals 4 to the x. So our base here is 4. So if I plug in values such as -2, 0, and 2, their output is, if I plug in -2, I get 4 to the -2nd, so I have to flip that to the bottom of the denominator, so 1 over 4 squared, which would be 1/16. If I plug in 0, anything to the 0 power is 1, and now 4 squared is positive 16. So let's go ahead and graph this over to the right on our graph. And our graph is on the right. Again, that's an exponential function. So let's name some of the properties of exponentials. And some properties here would be that we have an asymptote at y equals 0. And again, an asymptote is a line that a graph approaches. Here will never get to 0. That will get very, very close to 0, but as we plug in negative exponents, we won't actually ever get to 0. So asymptote again at y equals 0. And then these graphs always have a smooth curve. Always have one smooth curve to them. The domain for exponentials, in this case, it's all reals. So x is between -infinity and positive infinity. And the range here will vary. Y is strictly between 0 and positive infinity, again, because that 0 there is that asymptote. And this was just a brief review on exponential functions. Let's review exponential decay and exponential growth. So for exponential decay, as you can see in that blue graph on the right, that graph is decreasing, or we know as decaying. So this happens when your equation a is greater than 0 and b is between 0 and 1. So if I had an equation here and I have y equals a times b to the x for an exponential, this means that a would be, I'm going to fix this real quick, a would be greater than 0, so positive. So here, let's just say it's going to be 1. And then our base is between 0 and 1, so a fraction. So let's, think about 1/4 to the power of x. That graph we did in our notes, if you recall, the other day, and that graph was decaying. It was decreasing. Okay, so that's how we can recognize with an exponential function that we have decay when your graph is decreasing, or also b is between 0 and 1, and a obviously is greater than 0, so a is positive. Exponential growth occurs when a is greater than 0, again, okay, so it's positive, and b is greater than 1. So now, for our general exponential y equals a times b to the x, we are now going to say that a is 1 and b is going to be 4, so something greater than 1. And this was a function that we graphed the other day in our notes, and we just reviewed it, where it was growing, it was increasing. Okay, and so that's the difference between growth and decay. We'll talk about what negatives do a little bit later, but for right now, we can, figure out the general shape of our graph and know if it's growth or decay based on, either what the graph looks like or the equation that we're given. So now we are going to determine if the set of data has exponential behavior. So we're just going to look at data and see if it would be exponential. So the first method we could use is look for a pattern. When you look for a pattern with exponentials, you must have a common interval in the domain and must have a common factor in the range. So as we look at the x values, so between 0 and 2, 2 and 4, 4 and 6, 6 and 8, 8 and 10, there must be a common interval. So from 0 to 2, we're adding 2. From 2 to 4, we're adding 2, adding 2. So this is a good sign in that we're adding a common interval every time in the x's. But now let's determine the y's. There must be a common factor in the range. So here, we look from 64 to 32, 32 to 16, so on and so forth. From 64 to get to 32, we divide by 2, or we could say we are multiplying by 1/2. And as we start to look at this data, it's going to be easier for us down the road if we can change a division problem into multiplication. And again, that will help us down the road. So I'm going to say here, instead of dividing by 2, multiply by 1/2. And that happens between all of these successive terms. We're multiplying by 1/2, right? We're cutting the number in half. So this would, just because we have a common interval in the domain for the x's, right? And we have a common factor in the range for the y's, that this would show exponential behavior. So how we would write this for our answer is we would say yes, that this would show exponential behavior because there's a common interval in the domain and common factor in the range. And we do need to write out our answer like that. Okay, so that's one method to determine the behavior. If it's exponential, not very difficult. The second method would be if you don't want to look at that table and determine, you could also just graph. So does the graph show a smooth curve? Does it look like it would be exponential? So let's go ahead and graph those ordered pairs there to the graph on the right. So I just graphed a few of those data points on the graph, and as you can tell, it does not display a smooth curve at all, right? That's a straight line, so that's actually a linear. So I would say here, no, this would not display exponential behavior because it's a linear function. And you can actually determine that or see that now from the set of data if you had thought of that previously. So no, because it's a linear function. Okay, now let's talk about transformations for exponential functions. So right now I'm picking the parent function as y equals 5 to the x. Again, when we talked about, a parent function of exponentials, we always talked about y equals a times b to the x. However, if you're trying to determine transformations based on that, you won't get anywhere. And the reason for that is because you don't have anywhere to start. So for every time you answer questions about transformations, you will be given a parent function. And it could be different every time you see a new one, but we'll kind of, determine a set pattern for what we talk about as what would be, our parent function. So right now, our parent function is y equals 5 to the x. So let's take a look here at what certain transformations can do to exponentials. For a vertical shift up, so translating up so many units, that would be something like y equals 5 to the x. Again, you need your base in your function because that's your parent function, plus 3. That would allow that function to go up 3 units. A vertical shift down would be y equals 5x minus 3. And again, we need that 5 to the x in there because that's part of our parent function. All right, to go right or left, here's what you will see for an exponential. And again, we will review these on graphing calculators, but for right now, we'll just write down the notes. So for a transformation to go to the right, we would have something like y equals 5 to the power of x minus 4. So again, when we subtract, we go to the right, just like quadratics, right? It really goes the opposite way you might think. So that's when you have your exponent have x minus something, that means we go to the right. For translating left so many units, we would have y equals 5 to the x plus 4. So again, when you add with your exponent, you go to the left. All right, for a stretch or compress, that is the same idea as quadratics. So again, with a stretch, that was the absolute value of a being greater than 1. For a compress, the absolute value of a was between 0 and 1. So what this would look like here is y equals, again, I still have to have my base of 5 to the x, but now it's all about whatever is in front of my base, so whatever a is here, and a has to be greater than 1. So y equals, this could be like 2x to the 5th. Okay? And a compress, y equals, again, I would need 5 to the power of x somewhere in my equation. And this now needs to be a number between 0 and 1. So I could say a could be like 1/2. So any type of fraction, that would be between 0 and 1. So I'm just going to provide you a visual of what a stretch would look like with exponentials. So right here to the left of, so right here, this graph, that would show just y equals 5 to the x. So that black line, that graph would be just the parent graph. So here would be the y equals 2 times 5 to the x. This would be like a stretch, right? It would be jumping up at a faster rate than the parent function. So hence, stretch it. Can't really tell it's thinner here because we don't have a parabola to look at, but the slope definitely jumps up quicker. Same thing here with the compress. Okay, as if I have a graph right here and that's y equals 5 to the x, a compress means that our graph would have a slower or a wider slope, wouldn't be quite as steep as that parent function. Would still look like the same shape, but would just be wider. Okay, reflections. So for an x-axis reflection, we know that for quadratics, we would just need a negative in front of our, x squared term. Well, here, it's very similar. An x-axis reflection would look like y equals negative, and again, we need our 5 to the x, negative 5 to the power of x. That negative in front of our base means that we have a reflection. Now, for a y-axis reflection, we will see these quite a bit. Now with exponentials, we didn't see a whole lot with quadratics, but this looks like y equals 5 to the negative power of x. So that's when now our variable, our x variable, is negative. That would be a y-axis reflection. Now here's what the graph would look like if you had an x-axis reflection. So on that graph, I have y equals 5 to the x, just sketched. And over a reflection over the x-axis means I would reflect, obviously, over the x-axis. So it would be the same shape. It just opens downward. So this would be y equals negative 5 to the x. Okay, similarly with a y-axis reflection, I reflect over the y-axis. So same shape, nothing changes, I just reflect that over the y-axis. So what that will look like will be this. So as you can tell, same shape, just reflect over a certain axis. Thank you for listening. Have a great day. Please check Google Classroom for more information. Bye.